close your eyes and think of the ocean. Not the shore, not the waves breaking against the sand, not the water you see from the beach in summer. Think about what lies beneath. What lies far beneath. That world that begins where the sun's light ends and extends downward for miles, in a darkness so complete and so ancient that no human eye witnessed it for nearly all of our species' history. That's where we're heading tonight. The ocean covers 71% of Earth's surface. It is the most distinctive feature of this planet when viewed from space, the reason it appears as a blue sphere from far away. And yet, we know less about it than we do about the surface of the moon. We have mapped the moon in greater detail than the bottom of our own oceans. We have sent probes to Mars and Jupiter and to the edges of the solar system before we have even explored a fraction of what lies in the depths of the seas surrounding us. It is one of the strangest paradoxes of human exploration and also one of the most fascinating. Why? Because the deep ocean is hostile in a way that space is not, or not in quite the same way. In space, the problem is the void, the absence of pressure, the absence of air. In the deep ocean, the problem is the opposite, too much pressure. For every 33 feet of depth you descend in the water, the pressure increases by 1 atmosphere. At 3,000 feet deep, the pressure is of 100 atmospheres, 100 times the pressure of air at sea level. At the 36,000 feet of the Mariana Trench, the deepest known point in the ocean, the pressure is approximately 1,100 atmospheres. It's as if you had the weight of 50 passenger airplanes on top of you for every square inch of your body. Under those conditions, nothing that humans construct to move through air or space works. The materials we use in everyday life compress, deform, break. Water is not compressible, but solids are under sufficient pressures, and at the pressures of great depths even metal behaves in ways that engineers must calculate with extreme care. Designing a vehicle capable of surviving at the bottom of the Mariana Trench is an engineering challenge that rivals that of designing a spacecraft, with the difference that the ocean floor is much less accessible and much more difficult to study in real time. Only 3 people have ever reached the deepest point of the ocean, the Challenger Deep, in the Mariana Trench. The first time was in 1960, when Jacques Picard and Don Walsh descended aboard the bathyscaphe Trieste. They came back up without having been able to see almost anything because of the sediment their own propellers had stirred up. The second time was in 2012, when filmmaker James Cameron descended alone in his submarine deep-sea Challenger. And the third was in 2019, when explorer Victor Vescovo reached the bottom in his vehicle DSV limiting factor, setting a new depth record. 3 people. In all of human history, 3 people have reached the deepest point of our own planet. Compared to that, the moon seems almost accessible. 12 people have walked on its surface. The deepest point in the ocean has received exactly 3 visitors. And what those visitors found, what robots and probes and scientific instruments have gradually been revealing for decades of undersea exploration, is a world so strange and so rich and so full of surprises that every expedition returns with something that no one expected to find. The deep ocean is the last great unknown territory of Earth. And tonight we are going to explore it together, slowly, from here, with the sound of water as background and darkness as frame. To understand the ocean floor, you must first understand how it is structured, because it is not a uniform or simple space. It is a landscape as varied and as complex as any continental landscape, with mountains taller than the Alps and valleys deeper than any terrestrial canyon, with plains that extend for thousands of miles and active volcanoes and mountain ranges that encircle the entire planet. The part of the ocean most known to most people is the photic zone, the region where the sun's light reaches. It extends from the surface to approximately 650 feet deep, although that limit varies depending on water clarity, latitude, and time of year. In this zone, photosynthesis is possible, algae and phytoplankton produce energy from sunlight, and life flourishes with an abundance and diversity that make this band of water the biological engine of everything that exists below it. Most of the deep ocean's ecosystems depend, directly or indirectly, on the rain of organic matter that falls from the photic zone into the depths when surface organisms die and sink. Below 650 feet begins the mesopelagic zone, also called the twilight zone or the zone of dusk, which extends to approximately 3,000 feet. Some light still reaches here, but so little that it is insufficient for photosynthesis. The animals living in this zone have developed extraordinary adaptations to take advantage of that minimal light. Enormous eyes, often disproportionate to body size, capable of detecting the scarce photons that penetrate to that depth. Many of them perform daily vertical migrations, ascending toward the photic zone at night to feed and descending again under cover of darkness during the day, covering hundreds of feet of vertical distance twice a day in a cycle that is one of the most massive animal migrations on the planet, although it occurs completely invisibly to any observer on the surface. Below 3,000 feet begins the bathypelagic zone, the midnight zone, where darkness is absolute and permanent. Here the pressure is already 100 atmospheres or more. The water temperature hovers around 35 to 37 degrees Fahrenheit, with small variations depending on the region. There is no sign of the day-night cycle. Time, in the way we who live on the surface perceive it, simply does not exist here. There is pressure, there is cold, there is darkness, and there is life, which found in this apparently hostile environment not an obstacle but an opportunity. The abyssopelagic zone extends from 13,000 to 19,000 feet. Here are the Great Abyssal Plains, the largest terrains on Earth, larger than all continents combined. They are landscapes of fine sediment, accumulated over millions of years, so smooth and so calm that the footprints of animals walking on them can persist for centuries without being erased. They are also the places where organic matter from the surface takes the longest to arrive, and where organisms have had to develop the most efficient feeding strategies possible to survive with minimal resources. And finally, below 19,000 feet, is the Hadal zone, named in honor of Hades, the Greek god of the underworld. They are oceanic trenches, the places where one tectonic plate sinks beneath another and the oceanic crust descends toward the mantle. The Mariana Trench, the deepest of all, extends for about 1,600 miles in the western Pacific, with a maximum depth of approximately 7 miles at the Challenger Deep. But there are dozens of hadal trenches distributed throughout the world's oceans, each with its own ecosystem adapted to conditions that until just a few decades ago were considered incompatible with any form of life. This layered world, each layer with its own conditions, its own inhabitants, and its own rules, is what we are going to explore tonight. Not in the order a textbook would catalog it, but in the order someone would discover it by descending slowly, letting the darkness grow gradually around them, feeling how pressure increases and temperature drops and light fades until it disappears, and finding at each level new forms of life that defy what we thought was possible. Somewhere between 650 and 3,000 feet of depth, as the sun's light fades definitively, something begins to happen that has no equivalent anywhere else on Earth. Living beings begin to produce their own light. Bioluminescence, the production of light by living organisms through chemical reactions, is one of the most remarkable phenomena in the deep ocean. It is not common in places with abundant light, where the energy cost of producing light outweighs its benefits. But in the twilight zone, where light is scarce and precious, bioluminescence becomes not a luxury but a survival tool. Some organisms use it to attract prey. The anglerfish, perhaps the most famous example, is a small fish with a huge mouth and an elongated tooth-filled snout that looks more like a nightmarish alien than anything that should exist in the real world. Above its mouth hangs a modified fin ray that emits bioluminescent light, a living fishing rod that dangles before its face. Female anglerfish are larger, reaching up to 12 inches, while males are much smaller, rarely exceeding 1 inch. The males, which have underdeveloped eyes and a much smaller mouth, serve primarily a reproductive function. Once a male finds a female, he bites her and adheres to her body, gradually fusing with her until he essentially becomes an extension of her body, providing sperm when she needs to reproduce. From the female's perspective, it is a bargain. She gets a permanent supply of sperm at the cost of carrying around a small biological appendage. From the male's perspective, it is survival in an environment where food is so scarce that finding a mate more than once might be nearly impossible. But bioluminescence does not only serve to attract prey. Many organisms use it to communicate with each other. Fish flash patterns of light like Morse code, conveying information about their species, their reproductive status, their intention to mate or to avoid predation. Squid change colors rapidly across their bodies in waves of bioluminescent light, signals that are meaningless to us but that carry important information for other squid. Some bacteria produce bioluminescence only in the presence of large numbers of other bacteria, a phenomenon called quorum sensing that allows the bacterial population to coordinate its behavior. And some organisms use bioluminescence as a defense. When threatened, they produce sudden flashes of light that confuse or disorient their predators, creating an opportunity to escape. Others produce luminous clouds similar to a squid's ink cloud, except made of light-producing particles, a tactic that we do not fully understand but that appears to be an effective deterrent against attacks. The sight of a bioluminescent organism in the darkness of the deep ocean is something few humans have witnessed, and even fewer can adequately describe. Scientists who have spent years studying deep-sea life speak of it with a tone that sounds more like poets than researchers. There is something about the self-generated light in an environment where light should not exist, in an environment so cold and so dark and so alien, that transforms the act of seeing it into something almost transcendent. And these creatures produce their light every single night. Countless trillions of them, across millions of species, generating illumination in the darkness that has been occurring in the same way for millions of years before humans ever developed the technology to witness it. That light is happening right now, as you read this, as you close your eyes, as the sleep approaches. If you were to descend into that darkness, moving downward with instruments and cameras and lights adapted for the extreme environment, you would notice something remarkable. The deeper you go, the more light you see, not less. This counterintuitive observation is the result of the incredible concentration of bioluminescent organisms in the deep ocean. In the twilight zone, particularly between 2,400 and 3,300 feet, there is a layer of the ocean so densely populated with organisms that it appears as a false bottom to anyone looking up from the truly deep regions below. This is called the Deep Scattering Layer, or DSL, and from below, it appears as if the night sky has a visible, glowing floor. What creates this layer is abundance. At these specific depths, the conditions are optimal for a particular ecological niche. It is deep enough to offer some protection from the predators of the sunlit zone, but not so deep that food is impossibly scarce. The currents here bring together nutrients from both above and below. The pressure is intense but not yet so extreme as to limit the organisms that can survive. And the temperature is dropping but has not yet reached the near-freezing conditions of the truly deep ocean. So here, in these specific depths, life concentrates. Small fish by the millions, copepods numbering in the trillions, jellyfish, squid, and countless other organisms form a layer of such density that it was originally detected by sonar operators during World War II, who initially believed they had found something solid, a false bottom, not realizing they were detecting the backs of countless living animals. This layer migrates vertically with the sun. During the day, when there is more light penetrating from the surface and the danger from visually hunting predators is greater, the organisms of the DSL descend deeper, seeking refuge in deeper, darker waters. As night falls and the surface is plunged into darkness, the organisms rise up toward the surface waters to feed, taking advantage of the cover of darkness to enter regions where food is more abundant. This vertical migration, occurring simultaneously for millions of organisms over vast areas of the ocean, is the largest animal migration on Earth by biomass. Every day, trillions of organisms move hundreds of feet up and down, a movement so vast that it constitutes the largest displacement of biomass on the planet. And yet, virtually no one on land notices it. The ocean surface shows no sign of this movement. The sky shows no sign. The migration occurs in a realm that has been, until very recently, completely invisible to human observation. But the inhabitants of the DSL know about it. They coordinate their movements with each other, with their predators, with the availability of food. The movements are not random. The timing, the speed, the distance migrated all vary depending on the moon phase, the season, and the type of organism involved. On nights when the moon is full and bright, the organisms descend deeper than on new moon nights, seeking the shelter of greater darkness. After countless generations, evolution has encoded into their behavior an understanding of the patterns of light and darkness in the deep ocean, an understanding so precise that they can navigate a world where they cannot actually see the sun but know its position based on the qualities of light at their depth. And they do this night after night, season after season, year after year, in a cycle that has been occurring for millions of years. Your ancestors never knew this migration was happening. The vast majority of humans alive today have no awareness that at this very moment, as night falls over the ocean, trillions of organisms are beginning their ascent toward the surface, a movement that will last throughout the night and reverse as dawn approaches. But it is happening. And from the perspective of these organisms, this migration is not an oddity or a special behavior. It is the essential structure of their existence. Every night, they risk their lives and the lives of their companions by ascending into waters where food is more abundant but where predators are waiting. Every night, they make the same calculation, the same bet, the same choice. And every night, some of them lose. The creatures of the deep ocean have many extraordinary adaptations, but perhaps none more remarkable than the eyes of some of its inhabitants. In an environment where light is at a premium, where even a few photons can mean the difference between survival and starvation, the evolution of vision has taken some unusual and extreme paths. Some fish have eyes that face upward, toward the faint light coming from above, eyes designed specifically to detect the silhouettes of prey against the barely brighter surface. These eyes are enormous relative to the fish's body size, occupying a substantial portion of the fish's head, composed of millions of photoreceptor cells that are more sensitive to light than the eyes of any human ever could be. In some species, these eyes can rotate, turning to face the darkness below when the fish is actively hunting in the depths, then swiveling back to face upward to watch for the shapes of other organisms against the distant light of the surface. But some organisms have abandoned eyes entirely. In the absolute darkness of the abyssal plane, where not even the faintest bioluminescence reaches, vision is useless. The expenditure of energy needed to maintain eyes and the neural tissue needed to process visual information would be a waste in an environment where the eyes could never possibly perceive anything. So some species have evolved without them. Fish with no eyes, no eye sockets, just smooth skin where eyes should be, navigating and hunting in a world of absolute darkness using other senses. The lateral line, which detects vibrations in the water, the chemoreceptors, which detect chemical signals indicating the presence of food or mates, and possibly senses we do not yet fully understand. Instead of vision, some organisms in the abyssal zone rely on vibration. The lateral line system, present in all fish, is an array of sensory organs arranged in lines running along the fish's body, capable of detecting even tiny movements in the water. In an environment of absolute darkness, this sense becomes extraordinarily refined. A fish with a hypersensitive lateral line can detect the movement of another organism from considerable distances, can distinguish between the movement patterns of different species, can even detect the presence of a potential mate by the specific pattern of water displacement their movements create. Other organisms rely heavily on chemical signals. The ocean is a medium filled with molecules released by living organisms. Pheromones indicating reproductive readiness, amino acids released by dead and dying organisms, chemical signals indicating the presence of food. In the darkness, these chemical signals become as important as visual signals are in the sunlit world. Some deep-sea organisms have nostrils so large and nasal passages so sensitive that they can detect a single molecule of a relevant chemical compound in the water around them. A whale shark hunting in the darkness, moving along the ocean floor in search of a meal, might detect the presence of food by smell from miles away and follow the chemical gradient, moving closer and closer until it finds the source. These sensory capabilities, refined through countless generations of evolution in an environment unlike any other on Earth, seem impossible when viewed from the perspective of surface life. How could an organism evolve such sensitivity? But the answer is simple. Through the same process that gave humans our capacity for vision and language and complex thought. Given millions of years and an environment where a particular sensory capability provides a significant survival advantage, organisms will evolve that capability. The eyes of humans and the lateral lines of deep-sea fish and the chemical sensors of predatory sharks are all solutions to the same fundamental problem: how to navigate and survive in the environment you inhabit. In the depths of the ocean, that problem has been solved in ways that seem almost magical from the surface perspective, but that are simply the result of evolution working in an environment radically different from our own. One of the most famous deep-sea fish is a creature that seems to have been designed by an imagination gone wild. The viperfish is a small fish, rarely exceeding a foot in length, with teeth so large they do not fit inside its mouth. The fangs protrude upward and downward even when the mouth is closed, making the fish appear to be in a permanent grimace. The teeth are specially adapted, needle-like, extremely sharp, and spaced in such a way that they form a mesh through which other fish cannot escape once the viperfish has bitten down on them. But the teeth are not the most remarkable feature of the viperfish. Most remarkable is its body color. Black, so absolutely black that it appears to absorb light rather than reflect it. This black skin is an adaptation to the environment where the viperfish lives. In a world where organisms produce light through bioluminescence, where predators use that light to hunt, where any reflection of light could reveal an organism's position to a predator, being black is a survival advantage. It is camouflage in an environment where the camouflage is darkness itself. The viperfish is a predator, and like many predators in the deep ocean, it has adapted to an environment where food is scarce and must therefore never be wasted. When the viperfish catches another fish, it can unhinge its jaw, opening its mouth to a size that seems impossible given the fish's overall size, allowing it to swallow prey nearly as large as itself. The interior of the viperfish's mouth is bioluminescent, glowing with a faint light that may help lure prey in or may serve some other function we do not yet understand. When the viperfish has eaten, it returns to the normal routine of the deep ocean: hunting, avoiding being hunted, existing in the cold and the pressure and the darkness. A more surprising deep-sea predator is the Dumbo octopod, named for its ear-like fins that resemble the ears of the famous Disney elephant. The Dumbo octopod lives at even greater depths than many other creatures, sometimes at depths of over 3 miles, in an environment so cold and so dark that even many deep-sea organisms do not venture. The Dumbo octopod, despite being an octopod and therefore a relative of octopi capable of remarkable intelligence and behavior in shallower waters, appears to lead a life of simplicity in the deep. It crawls slowly along the ocean bottom, feeding on whatever organic material it encounters, taking bites of sediment and processing it to extract nutrients. Some Dumbo octopi have been observed and filmed, and scientists have noted that these creatures seem almost fragile, almost gentle, despite being in one of the harshest environments on Earth. They do not seem to be efficient hunters in the aggressive sense. Instead, they are gatherers, moving slowly through an environment where passive feeding is apparently more successful than active hunting. In a world where food is so scarce that energy expenditure must be minimized, the Dumbo octopod survives through patience and efficiency rather than speed and aggression. These creatures, and the countless others that inhabit the deep ocean, are not monsters in any meaningful sense. They are solutions. They are the products of millions of years of evolution in an environment where the challenges are extreme and the resources are limited. They have adapted to solve the problems posed by that environment, and in doing so, they have become some of the most remarkable organisms on Earth. To call them monstrous is to miss the point. To call them remarkable is to understand them correctly. Deep in the ocean, below the zones where multicellular life dominates, there exists a world that most people never consider. The world of bacteria and archaea, single-celled organisms that constitute the vast majority of life on Earth by numbers and by biomass. These organisms are found everywhere in the ocean, from the surface to the deepest trenches, from the hottest hydrothermal vents to the coldest, most stable waters of the abyssal plains. For most of human history, bacteria were thought to be simple, primitive organisms, essentially just bags of chemicals floating in water. The bacterial cell was thought to be a more primitive version of the cells that make up plants and animals. But as microscopy has improved and as we have developed techniques to study bacterial behavior, we have come to understand that bacteria are remarkably complex, capable of remarkable sophistication and even what might be called problem-solving. Bacteria in the deep ocean engage in behaviors that would have been thought impossible in earlier eras. They form communities called biofilms, where thousands or millions of individual bacteria adhere to each other and to surfaces in the ocean, creating structures that are protected from the surrounding environment and that allow the bacteria to share resources and information. Within these biofilms, bacteria can regulate their behavior based on the behavior of their neighbors, adjusting their own genetic expression in response to chemical signals from other bacteria. This process, called quorum sensing, allows a population of bacteria to coordinate behavior across the entire community, turning on genes involved in cooperative behaviors like bioluminescence only when enough bacteria are present to make those behaviors worthwhile. In the depths of the ocean, bacteria are also the primary players in the cycling of nutrients that makes life possible. The organic matter that rains down from the surface regions of the ocean, the dead bodies of plankton and fish and other organisms, settles on the ocean floor. But it does not stay there indefinitely. Bacteria and other microorganisms break it down, consuming it, oxidizing it, releasing the nutrients locked in the organic matter back into the ocean. Without this bacterial recycling, the nutrients that support surface life would be locked away in the depths, and surface productivity would collapse. The ocean would still look the same from above, but it would be biologically dead. But bacteria in the deep ocean do more than just recycle dead organic matter. Some bacteria have evolved the ability to obtain energy from unusual sources. Chemosynthetic bacteria, found particularly in the vicinity of hydrothermal vents, obtain their energy not from the sun but from chemical reactions involving hydrogen sulfide and oxygen. In the areas around hydrothermal vents, where hot mineral-rich water is expelled from the ocean floor, these chemosynthetic bacteria form the base of an entirely separate ecosystem, a second tree of life on Earth that does not depend on the sun at all. Most of the Earth's surface productivity is based on photosynthesis, the conversion of sunlight into chemical energy. But in the deep ocean, particularly at hydrothermal vents and in some other deep-sea environments, chemosynthesis takes over. The bacteria obtain energy from chemical reactions, and other organisms feed on these bacteria, and predators feed on those organisms, and an entire food web develops that is completely independent of the sun. For much of Earth's history, before photosynthesis evolved or before photosynthetic organisms had invaded all the ocean's regions, chemosynthesis may have been the dominant form of energy acquisition. The discovery of chemosynthetic ecosystems in the deep ocean has completely changed how scientists think about the possibility of life on other planets and in other environments previously thought to be impossible for life to exist. These microscopic organisms, invisible to the naked eye, are perhaps the most important organisms in the deep ocean. They maintain the chemical cycles that make complex life possible. They thrive in environments that would kill most other organisms. And they do so with a simplicity and an efficiency that is breathtaking to contemplate. Among all the creatures of the deep ocean, few are as fascinating or as misunderstood as the giant squid. For centuries, the giant squid occupied a space in human imagination somewhere between reality and myth. Sailors spoke of them as sea monsters, krakens capable of dragging ships down into the depths. But scientific understanding of the giant squid remained limited until very recently, because the giant squid itself was very difficult to study. Giant squid live at great depths, generally between 3,000 and 6,000 feet, in the cooler waters of the deep ocean. They are carnivorous, feeding on fish and other squid. They can grow to enormous size, with some specimens reaching over 40 feet in length, with enormous eyes that are among the largest eyes of any animal on Earth, eyes as large as dinner plates, capable of seeing in the dim light of the deep ocean. For a very long time, the only information scientists had about giant squid came from specimens that had washed up on beaches, often in poor condition after death and decomposition. Finding a living giant squid was almost unheard of. The creature seemed to actively avoid human observation. Dead specimens would occasionally be found, sometimes providing valuable information, but living squid of this species remained essentially unknown. Then, in the year 2004, something changed. Off the coast of Japan, in deep waters, a squid was caught and brought to the surface alive. This was a significant event, important enough that scientists were contacted and a decision was made to film the creature and then release it back into the ocean. The footage that resulted from this filming is extraordinary. A living giant squid, moving with evident grace and power, its body shifting colors, its enormous eyes rotating to look at the camera, a creature that existed not as myth or as a decomposed corpse but as a living being. Since then, other encounters with living giant squid have been documented, most through deep-sea cameras deployed to observe the abyssal environment. These films reveal an animal that is intelligent, that appears to be curious, that has behaviors and capabilities that scientists are still working to understand. Giant squid hunt in the darkness using a combination of vision, chemoreception, and possibly other senses. They navigate through a three-dimensional environment, hunting mobile prey in a zone where food is scarce. They are highly successful predators despite the challenges of their environment. But giant squid are not the largest squid in the ocean. That distinction belongs to the colossal squid, a creature that lives in the Antarctic waters and that is even larger than the giant squid, with thicker, more powerful arms and a body mass that can exceed that of a large elephant. Very few humans have ever seen a living colossal squid, and much of what we know about this creature comes from specimens that have washed up dead or that have been found in the stomachs of sperm whales, the primary predator of the colossal squid. The relationship between sperm whales and colossal squid is one of the most dramatic predator-prey relationships in the ocean, perhaps in the world. Sperm whales are enormous, among the largest toothed whales, capable of diving to extraordinary depths in pursuit of their prey. Colossal squid have huge tentacles lined with suckers and hooks. The encounters between these two creatures, which must occur in the darkness of the deep ocean at depths that no human has witnessed directly, can only be imagined based on the scars that surface on both combatants when they are observed. Sperm whales bearing the marks of squid hooks, colossal squid bearing the marks of whale teeth. Both predator and prey marked by their encounters with each other. These encounters are not casual hunts. They are battles between two of the most formidable creatures in the ocean, battles that result in the death of one of the two combatants. To what extent either creature experiences these battles consciously, with fear or pain or determination, remains unknown. But from the perspective of the human observer, trying to understand the lives of these creatures from a distance, the drama is clear and the stakes are real. One of the most significant discoveries in deep-sea science came in 1977, when a research team led by Robert Ballard, best known today for his discovery of the wreck of the Titanic, was exploring a region of the Pacific Ocean near the Galapagos Islands. They were searching for geological features called hydrothermal vents, areas where water seeping down through cracks in the ocean crust is heated by the Earth's interior and returned to the ocean floor as hot, mineral-rich water. Previous theories suggested that these vents would be lifeless, or nearly so. The water from hydrothermal vents is extremely hot, often exceeding 750 degrees Fahrenheit, far hotter than any temperature at which most organisms are known to survive. But what the research team found when they reached the vents was completely unexpected: a thriving ecosystem. Around the vents, the water cooled as it mixed with the surrounding ocean water, creating a gradient from scalding heat near the vent opening to cold, normal ocean temperature at some distance away. And along this gradient, life flourished. Bacteria colonized the surfaces of rocks near the vents, deriving their energy directly from the chemical reactions between the hot vent water and the surrounding cold ocean water. These bacteria, while invisible to the naked eye, formed the base of a food web that supported much larger, more visible organisms. Among these organisms were giant tube worms, creatures that seemed impossible. Tube worms at these depths and in shallow water are typically quite small. But the tube worms of the hydrothermal vents grew to enormous size, some reaching 8 feet or more in length, forming dense colonies around the vents. The tube worms have no mouth and no stomach. Instead, they maintain a symbiotic relationship with chemosynthetic bacteria that live inside their tissues. The bacteria obtain energy from hydrogen sulfide in the vent water, and the tube worms benefit from the energy produced by the bacteria. The tube worms provide the bacteria with a safe environment and transport them to sources of fresh chemical energy. In return, the bacteria keep the tube worms alive. This relationship was revelatory. Before the discovery of hydrothermal vent ecosystems, scientists believed that virtually all life on Earth derived its energy ultimately from the sun, through photosynthesis. The existence of entire ecosystems based on chemosynthesis, on energy derived from geological processes rather than solar energy, meant that the fundamental assumptions about how life on Earth works needed to be revised. The implications were profound. If entire ecosystems could develop around hydrothermal vents on Earth, could they exist around hydrothermal vents on other planets or moons? Could life exist on Europa, the moon of Jupiter, which is believed to have liquid water beneath its icy crust? Could it exist on other bodies in the solar system where liquid water is present but where no sunlight penetrates? The discovery of hydrothermal vent life suggested that the boundaries for what environments could support life were much broader than previously thought. Since the initial discovery, hundreds of hydrothermal vents have been located on the ocean floor. Each vent system supports a unique ecosystem, with some variations in the dominant species depending on the specific chemistry of the vent water and the broader oceanographic conditions of the region. In some vents, tube worms are dominant. In others, mussels or crustaceans or unusual species of fish dominate. But in all of them, the fundamental pattern is the same. Chemosynthetic bacteria at the base of the food web, supporting larger organisms that exist nowhere else on Earth. And this entire ecosystem, with all its complexity and its diversity, exists in complete darkness, at pressures that would crush any human instantly, at temperatures that vary between near freezing and boiling in the space of a few feet, in an environment that would have been thought completely hostile to life not long ago. The creatures that live around hydrothermal vents represent an extreme adaptation to a specific environment, but they are not alone in their specialization. Throughout the deep ocean, different organisms have developed equally dramatic adaptations to their specific niches. Some of these adaptations are so specialized that the organism is dependent on conditions found nowhere else on Earth. The Dumbo octopi, mentioned earlier, provide one example of this extreme specialization. Their body structure, their metabolism, and their feeding strategies are all finely tuned to life at extreme depths. An organism that lives only at depths of 3,300 feet or greater, in temperatures just above freezing, feeding on the sparse organic matter that drifts down from above. This organism could not survive in the more abundant and more competitive environment of the shallower ocean. It has evolved to fill a specific niche, and in doing so, it has become entirely dependent on the continuation of the conditions that define that niche. This is true of many deep-sea organisms. They are specialists. They have evolved to do one thing very well: to survive in the specific conditions of their particular depth zone, under the specific pressure, at the specific temperature, in the specific light conditions. This specialization is an advantage in a stable environment where the organism faces little competition and consistent resource availability. But it is also a vulnerability. If the conditions of their environment change significantly, if the temperature rises or the pressure somehow decreases or the nutrient flow from above changes, these specialized organisms may find themselves unable to adapt. Which brings us to one of the great challenges facing the deep ocean today. The ocean is warming. This is not speculation or conjecture. This is documented fact, measured carefully using instruments and confirmed through multiple lines of evidence. The average temperature of the ocean surface has increased by approximately 1.08 degrees Fahrenheit over the past century and a half, with the rate of warming accelerating in recent decades. But the warming is not limited to the surface. The heat absorbed by the upper layers of the ocean is slowly diffusing downward, warming the deeper layers as well. The deep ocean is not warming as quickly as the surface, but it is warming. And this warming, while it might seem small in absolute terms, represents a significant change in an environment where temperatures have been stable for millions of years. The organisms that live in the deep ocean have no evolutionary experience with rapid temperature changes. They have adapted to cold that is stable and predictable. A rapid change in temperature, even a change of a few degrees, can disrupt the delicate balance of their physiology. Additionally, the ocean is becoming more acidic. As atmospheric carbon dioxide levels rise, more carbon dioxide dissolves into the ocean, forming carbonic acid. This process, called ocean acidification, lowers the pH of seawater, making it less basic and more acidic. This change affects organisms that depend on calcium carbonate for their shells or skeletons. Pteropods, small swimming snails that are important food sources for many deep-sea fish and for whales, are particularly vulnerable to ocean acidification. As seawater becomes more acidic, the shells of pteropods begin to dissolve even while the animal is still alive. These changes, warming and acidification, are happening simultaneously. They are happening at a rate far faster than the deep ocean has experienced in millions of years. And they are happening in an environment that is particularly vulnerable to such changes because so many of its organisms are specialized to the precise conditions that existed in the past. This is not a distant problem or a theoretical concern. It is happening now. The deep ocean, so stable for so long, is changing. Before discussing the human impacts on the deep ocean, it is worth understanding just how isolated the deep ocean has been from human activity for most of history. For thousands of years, humans have fished the oceans. We have taken whales and fish and other resources, sometimes sustainably and sometimes not. But the deep ocean, the real deep ocean beyond the reach of traditional fishing nets and lines, was essentially untouched. No human technology extended deep enough to significantly impact organisms living beyond a few hundred feet of depth. The deep ocean existed in a kind of separate realm, influenced by human activity only in the most indirect ways. This isolation has ended. The technology that allows humans to observe the deep ocean, to send down submarines and cameras and scientific instruments, also allows us to harvest resources from the depths. Deep-sea fishing has become a major industry in recent decades. Long lines baited with hooks stretch for miles along the ocean floor, catching fish at depths that were unreachable just decades ago. Fishing trawlers drag nets along the bottom of the ocean, scooping up everything in their path and often destroying the delicate habitats they encounter. The creatures of the deep ocean, having evolved in a world where they faced no predation pressure from humans, are particularly vulnerable to this new fishing pressure. Many deep-sea fish have low reproductive rates. They grow slowly, reaching sexual maturity late in life, and produce relatively few offspring. These are adaptations to an environment where food is scarce and where rapid population growth would quickly deplete available resources. But these same adaptations make them vulnerable to overfishing. When humans begin catching deep-sea fish faster than they can reproduce, populations decline rapidly. Some species have been fished to near extinction in the time that humans have been actively fishing for them, a span of just a few decades. Additionally, deep-sea ecosystems are particularly fragile because they operate at the edge of what is possible biologically. The organisms that live there are pushed to the limits of adaptation, living under conditions of extreme pressure and cold and darkness. The ecosystems themselves are supported by very thin threads of energy flowing from above. When those threads are disrupted, when the organisms that are crucial links in the food chain are removed by fishing, the entire ecosystem can collapse. But fishing is not the only way that humans are impacting the deep ocean. There are proposals for deep-sea mining, the extraction of valuable minerals from the ocean floor. Some of the richest deposits of rare earth elements, elements that are crucial for many technologies that modern civilization depends on, exist on the ocean floor. If these deposits are mined, it would involve dredging up material from the ocean floor, processing it to extract the valuable elements, and discarding the remainder. The impact of such mining on the ecosystems of the deep ocean would be catastrophic. The simple act of dredging across the ocean floor would destroy decades or centuries of sediment accumulation, would kill every organism in the area, and would likely disrupt sediment and water conditions for much larger areas around the mining zone. Additionally, human activity in the atmosphere is affecting the deep ocean in ways that we are only beginning to understand. Carbon dioxide is accumulating in the atmosphere, warming the planet and increasing ocean temperatures. The ocean absorbs this extra heat, slowly distributing it downward to deeper layers. At the same time, ocean acidification, also caused by increasing atmospheric carbon dioxide, is changing the chemistry of seawater in ways that affect organisms throughout the ocean, from the surface to the depths. These impacts, in their various forms, represent an unprecedented challenge for the deep ocean. For millions of years, the deep ocean has evolved in isolation from human influence. The organisms that live there have adapted to the precise conditions of that environment. But now, in the span of just a few decades, all of those conditions are changing simultaneously. The deep ocean is being fished, is being warmed, is being acidified, and is threatened with mining and other forms of extraction. The isolated world that created such extraordinary diversity of life now faces threats that it has no evolutionary experience in dealing with. In 1985, Robert Ballard, the same scientist who discovered hydrothermal vent ecosystems, made another of the most famous discoveries in the history of ocean exploration. He found the wreck of the RMS Titanic resting on the bottom of the Atlantic Ocean at a depth of approximately 12,000 feet. The discovery was significant for many reasons. It confirmed that the depth of the Atlantic at that location was sufficient to accommodate the largest ship ever built sinking to the bottom. It provided the first visual confirmation that the Titanic had indeed sunk, that it had not been salvaged and hidden but had instead spent nearly 70 years resting on the ocean floor. It solved mysteries about how the ship had gone down, as evidence gathered from the wreck showed that the ship had broken apart as it sank, contrary to the popular assumption that it had gone down intact. But the Titanic wreck also demonstrated something else. It showed that the deep ocean could be accessed by human technology, that it could be explored and documented. The cameras and submarines that Ballard used to explore the Titanic opened up a new era of deep-sea exploration. Within years of the Titanic discovery, thousands of hours of footage of the deep ocean had been filmed, ecosystems had been studied, new species had been discovered. The deep ocean was no longer completely unknown. It was becoming known through the lens of cameras and the eyes of robots. The Titanic wreck itself has become a kind of ecological study in this process. In the years since it was discovered, the wreck has been colonized by deep-sea organisms. Bacteria have broken down much of the ship's structure. Specialized organisms that feed on iron have stripped some of the metal. The wreck, which was a dead human structure when it sank, has become a living artificial reef, a place where deep-sea organisms have found a habitat where they can survive. In some ways, the Titanic wreck is a smaller version of what happens when any large structure is placed on the ocean floor. Ships are not the only human structures in the ocean. There are cables, pipelines, drilling platforms, and countless other structures that humans have placed on or near the ocean floor in the course of extracting resources or transporting materials and information. Every one of these structures becomes a substrate upon which deep-sea organisms can colonize. Some of this colonization can be beneficial, turning human structures into unintended artificial reefs. But often it is destructive, or at least deeply disruptive, to the natural ecosystems that existed before the human structures arrived. The presence of human structures on the ocean floor also changes how we think about the ocean. For thousands of years, the ocean floor was truly unknown, truly wild, existing in a state that was essentially untouched by human activity. Now, the deepest parts of the ocean have human presence. Not human life, not permanent human settlement, but human evidence. Structures that humans built for our own purposes, sitting on the bottom of the ocean, visible to cameras, altering the local environments around them. The ocean floor is no longer truly wild. It is a landscape that is being shaped by human activity, even if that activity is not always intentional or direct. The sperm whale, one of the largest and most powerful creatures in the ocean, is also one of the deepest diving mammals. Sperm whales regularly dive to depths of 6,000 feet or more, pursuing their primary prey, the squid that lives in the deep ocean. These dives last for over an hour, during which the whale's body undergoes remarkable changes. As a sperm whale begins its descent, several physiological processes activate. The whale's heart rate slows dramatically, a process called bradycardia, which conserves oxygen. Blood flow is redirected away from less essential organs and toward the brain and heart, the organs that are most critical for survival. The blood itself contains myoglobin, a protein similar to hemoglobin in humans, that stores oxygen and makes the blood appear dark red or black. The muscles of the sperm whale contain myoglobin as well, giving them a dark appearance and allowing them to store large reserves of oxygen. The sperm whale's body is also compressible in ways that human bodies are not. Air sacs in the lungs collapse as the whale descends and the pressure increases, preventing nitrogen from being absorbed into the bloodstream at rates that would cause the bends, a dangerous condition that affects human divers. Adaptations in the spine and ribs of the whale allow the skeleton to flex and move in ways that reduce stress from the enormous pressure. The eye of the sperm whale, immense and adapted to see in darkness, is built to withstand pressures that would crush a human eye instantly. Sperm whales have learned, through countless generations of evolution, how to exploit the deep ocean in a way that no human has managed. A whale does not need a submarine or a pressure suit or any technology at all. The whale's body is the technology, refined and perfected through millions of years of evolution. And because of this, the whale can pursue prey into the depths of the ocean with an efficiency that no human hunter could ever match. But the deepest diving marine mammal is not the sperm whale. That distinction belongs to the Cuvier's beaked whale, which has been recorded diving to depths of over 10,000 feet, approaching the deepest regions of the mesopelagic zone. The Cuvier's beaked whale is smaller than the sperm whale, with less need for large quantities of food, and with an even more efficient physiology for deep diving. The deepest recorded dive of any Cuvier's beaked whale lasted over an hour, during which the whale descended to depths of over 11,000 feet and then ascended again, all on a single breath of air. The feat is nearly incomprehensible from the perspective of human physiology. These diving mammals represent an extreme adaptation to the deep ocean environment. They are the only large, warm-blooded creatures that regularly venture into the depths. Their success in this environment is the result of millions of years of evolution, countless tiny improvements and adaptations accumulated over time. They are not modern innovations. They are time-tested designs, refined by evolution until they are nearly perfect for the role they play. And yet, even these remarkable creatures are facing challenges from human activity. Sperm whales and Cuvier's beaked whales are both impacted by underwater noise from human sources. Ships create noise. Sonar systems create noise. These sounds propagate through the water and can interfere with the whale's own sensory systems, the echolocation and hearing that allow them to navigate and hunt in the darkness. Some whale populations have shown increased rates of stranding, washing up on beaches in apparent distress, potentially caused by disorientation from underwater noise. The sperm whales and beaked whales also eat deep-sea squid, some of which are now being targeted by commercial fisheries. As these squid populations are depleted by fishing, the whales find fewer prey available, forcing them to dive deeper and longer in search of food. The whales that have adapted to exploit the deep ocean now find that the deep ocean is being exploited by humans in ways that threaten their survival. The pressure of the deep ocean is perhaps the most essential characteristic of the deep-sea environment, the factor that shapes everything about deep-sea life more than any other single feature. Pressure at great depths is not something that exists in a way that surface organisms can easily understand or relate to. A human body at depth experiences pressure not as a weight or a force, but as an environment. Every atom of the body is pressed equally from all directions by the surrounding water. The sensation is not one of pain or discomfort, necessarily, but rather a change in the fundamental nature of the environment. At extreme depths, water itself begins to behave differently. Water is generally considered incompressible, meaning it cannot be squeezed to a smaller volume by applying pressure. But this is only true of relatively modest pressures. At the extreme pressures of the deepest ocean, water does compress, slightly but measurably. This compression changes the properties of water, altering the speed at which sound travels through it, changing how heat is distributed, affecting all of the chemical reactions that occur in organisms living in that environment. pressure affects the size of organisms. The largest creatures on Earth live in the surface ocean or on land. In the deep sea, there is a trend toward smaller bodies in general, with some notable exceptions. This is partly because smaller bodies require less food, and food is scarce. But it is also because a smaller body presents less surface area to be damaged by pressure, requires less structural reinforcement to maintain its shape under pressure, and is more maneuverable in an environment that does not support large predators or large prey. The exceptions to this trend toward smaller size are instructive. The giant squid and colossal squid are enormous, among the largest invertebrates in the world. But they live in an environment where they are the apex predators, where there is no need to be small to avoid being eaten. Their size is a predatory advantage, allowing them to overpower their prey and to dominate their environment. Similarly, sperm whales, the largest toothed whales, are enormous, and that size is an advantage in their role as the apex predator of the deep ocean, the hunter that hunts hunters. The pressure of the deep ocean also affects metabolism. Many deep-sea organisms have metabolic rates that are far lower than surface organisms of similar size. This is an adaptation to the scarcity of food. By reducing the rate at which they consume energy, these organisms can survive for longer on smaller quantities of food. A deep-sea fish might move slowly, rest for long periods, and feed rarely, all adaptations that minimize energy expenditure in an environment where food is scarce. Over the course of a year, such an organism might consume only a fraction of the food that a surface fish of similar size would consume. But this low metabolism comes with a cost. It means that growth is slow, sexual maturity is reached late in life, reproduction is infrequent, and population recovery from overfishing is extremely slow. It means that these organisms are particularly vulnerable to changes in their environment, because they have limited capacity to adapt by changing their behavior or physiology. They are locked into a specific lifestyle by their extremely efficient adaptation to a specific set of conditions. The pressure of the deep ocean is therefore not merely a feature of the environment. It is a fundamental constraint that shapes every aspect of deep-sea life, from body size to metabolic rate to reproductive strategy. Understanding the deep ocean requires understanding pressure, and understanding the vulnerability of deep-sea organisms requires understanding how they have adapted to pressure in ways that leave them few options for responding to changes in their environment. The life history of a deep-sea organism is often radically different from the life history of a surface organism, not just in the strategies used to survive, but in the basic structure of how a lifetime is lived. A surface fish might reach sexual maturity within a few years, spawning multiple times in its life, producing thousands or millions of eggs, most of which die before reaching adulthood. This strategy, which biologists call R selection, trades quantity for quality, betting that enough offspring will survive to reproductive age to maintain or grow the population. A deep-sea fish, by contrast, might not reach sexual maturity for 10 or 20 years. When it does reproduce, it might produce only hundreds or thousands of eggs, not millions. It might spawn only once every few years. It invests much more energy in each individual offspring, increasing the chances that each egg will develop into a viable fish. This strategy, which biologists call K selection, trades quantity for quality, betting that fewer larger investments in each offspring will be more successful in a harsh environment than a large number of small investments. The result of these different strategies is that deep-sea fish populations recover from overfishing much more slowly than surface fish populations. If a population of shallow water fish is heavily fished, the remaining fish might recover the population within a few years through rapid reproduction. If a population of deep-sea fish is heavily fished, it might take decades or centuries for the population to recover, if it recovers at all. This is one of the reasons that deep-sea fisheries have been so destructive. The organisms that are being fished were not evolved to handle the pressure of human harvesting. They have no evolutionary experience with being hunted by creatures far more efficient than any natural predator. When humans arrive with industrial fishing technology, the populations can be devastated. But life history in the deep ocean is not determined only by energy constraints. It is also shaped by the extreme isolation of many deep-sea organisms. In the surface ocean, organisms can drift with currents and find new areas to colonize. But many deep-sea organisms, particularly those that live on the ocean floor, have limited larval stages. The larvae, instead of drifting in the currents for months or years, hatch with limited ability to disperse and settle near their parent. This means that populations of deep-sea organisms tend to be localized, separated from other populations by barriers of deep water or extreme depth. Each population is isolated, evolving independently, subject only to its own internal genetic variation and the selection pressure of its local environment. This isolation has led to the evolution of remarkable levels of endemism, the tendency of organisms to be found in one place and nowhere else. Some deep-sea organisms are found only in a single hydrothermal vent system, an area sometimes just a few hundred meters across. If that vent system is destroyed by human activity or by natural processes, the species that are endemic to that system would go extinct. And we would likely never know about them, because many deep-sea species have not yet been discovered, let alone studied or named. The combination of low reproductive rates, late sexual maturity, high endemism, and limited dispersal ability means that deep-sea organisms are particularly vulnerable to extinction. They cannot recover quickly from overharvesting. They cannot easily recolonize areas that have been damaged. They exist in small, isolated populations that have little genetic diversity and little capacity to adapt to environmental changes. For all of these reasons, the deep ocean, despite being isolated and unknown, is one of the most vulnerable ecosystems on Earth. The dark zones of the ocean have been colonized by life in ways that surface organisms might find almost incomprehensible. In regions of the ocean where light never penetrates, where food is scarce, where pressure is extreme, organisms have not merely survived but have flourished, developing complex behaviors and specialized structures that rival the complexity of surface life. One of the most remarkable features of deep-sea life is the phenomenon of bioluminescence, which we discussed earlier, but which deserves a deeper exploration. Bioluminescence is the production of light by living organisms through chemical reactions. In the surface ocean, bioluminescence is relatively rare and is generally found in small organisms like dinoflagellates or in the light organs of larger predators. But in the deep ocean, bioluminescence becomes a dominant feature of the environment. Perhaps 90% of deep-sea organisms produce light or can see light that others produce. The chemical reactions that produce bioluminescence in most marine organisms involve a molecule called luciferin and an enzyme called luciferase. The luciferin is oxidized by the luciferase, producing light as a byproduct of the chemical reaction. In some organisms, the luciferin is produced internally. In others, it is obtained from food, incorporated into the organism's own tissues, and then used internally to produce light. Some organisms have even developed symbiotic relationships with bioluminescent bacteria, housing colonies of bacteria in specialized light organs and using the bacteria's bioluminescence as if it were their own. The uses of bioluminescence in the deep ocean are diverse and complex. Predators use it to hunt, dangling a light in front of their mouth to attract prey. Prey use it to confuse predators or to communicate with potential mates. Some organisms use bioluminescence for a process called counterillumination, producing light on their undersides to match the faint light coming from above, effectively rendering themselves invisible to predators looking up from below. But bioluminescence is not merely a survival tool. There is growing evidence that bioluminescence in the deep ocean is also a form of communication, a language of light that allows organisms to exchange information about territory, reproductive status, threat, and opportunity. The patterns of light produced by deep-sea organisms are not random. They are often species-specific, with different species producing different patterns. These patterns might be read and interpreted by other organisms of the same species, allowing for complex behavioral responses. This means that the deep ocean, despite being completely dark to human eyes, is actually filled with communication, with signals being sent constantly from organism to organism. It is not a silent world, though there is silence in the sense that the sound frequencies that humans can hear are rarely produced in the deep ocean. But in the frequencies that deep-sea organisms can perceive, The deep ocean is anything but silent. It is filled with signals and responses, with a constant chatter of organisms communicating with each other. And all of this light, all of this communication, has been happening for millions of years, completely invisible to humans. The entire evolutionary history of bioluminescent signaling in the deep ocean happened without any human witnessing it, without any human even knowing it was occurring. Only in the last few decades, with the advent of cameras and submarines capable of operating in the deep, have humans begun to understand the rich visual communication system that has existed in the darkness all along. If you were to compile a list of the most extreme organisms on Earth, the organisms that have adapted to the most hostile environments, many would be found in the deep ocean. But not all. Some of the most extreme organisms are found in other parts of the ocean, or in completely different environments, but have adaptations that rival those of the deepest deep-sea creatures. The hagfish is one such organism. Hagfish are primitive fish, more ancient in evolutionary terms than most other fish, existing in forms similar to their modern descendants for hundreds of millions of years. They are ugly in the aesthetic judgment of humans, with no proper eyes, with a mouth that is more of a circular opening filled with tooth-like structures, with a body that seems almost boneless, more like a slug or a worm than a proper fish. But hagfish are not organisms that should be pitted for their apparent weakness. They are extremely successful, occupying ecological niches in the ocean and having survived unchanged for longer than most other fish groups. And they have an extraordinary defense mechanism. When threatened, a hagfish produces slime, an extremely thick mucus that covers its body and fills the surrounding water. This slime is not just sticky or unpleasant. It is a sophisticated defense that works in multiple ways. It clogs the gills of potential predators, making it difficult or impossible for them to breathe. It makes the hagfish itself nearly impossible to grip, sliding right out of a predator's mouth if the predator manages to catch it. And some studies suggest that the slime might even be toxic to some predators, or at least extremely unpleasant to consume. The hagfish's slime is an example of a defense that uses chemistry rather than speed or strength or size. And chemistry is a common tool in deep-sea defense. Many deep-sea organisms produce toxins, poisons, or other chemical compounds that make them unpalatable to predators or dangerous to consume. Some produce bioluminescent displays that startle or disorient predators. Others produce lures or other deceptions that trick other organisms into exposing themselves to danger. Another example of an extreme adaptation is the barrel-eye fish, which has a completely transparent head with eyes that can rotate to look upward or forward. This adaptation allows the fish to look upward through its transparent head to detect the silhouettes of prey against the faint light coming from above, or to rotate its eyes forward to watch prey directly. The fish is small, just a few inches long, but the adaptation is so specialized that it represents one of the strangest modifications of the basic fish body plan. These extreme adaptations, and countless others, represent solutions to specific problems posed by living in extreme environments. The hagfish's slime solves the problem of being small and slow in an environment with large, fast predators. The barrel-eye's transparent head solves the problem of having to watch for predators and prey in an environment where both are nearly invisible. Every extreme organism is an extreme solution to an extreme problem. What is remarkable is that these solutions have evolved not in the most favorable environments on Earth, not where conditions are easiest, but in the harshest, most unforgiving environments. The deep ocean, the Arctic, the Antarctic, deep caves, hot springs, the abyssal zones of the Earth, these are the places where evolution has produced the most extraordinary innovations. As if adversity itself drives creativity, as if hostile environments force organisms to develop new strategies and new structures that would never evolve in safer, easier circumstances. The whale fall is a remarkable phenomenon that occurs when a large whale dies and sinks to the ocean floor. For the organisms of the deep ocean, a whale fall represents an extraordinarily abundant food source, an event of such magnitude that entire communities of organisms have evolved specifically to exploit whale falls. When a whale dies at sea, the body sinks. As it sinks, it is attacked by scavengers. Sharks, hagfish, crabs, and other organisms consume the soft tissue of the whale. But the sinking process takes time, especially for very large whales, and the deep ocean is below the reach of most of these scavengers. A whale body sinking to the deep ocean floor can remain largely intact during its descent. When the whale reaches the abyssal plain, resting on the ocean floor at depths of 3,000 feet or more, a specialized community of scavengers takes over. Sleeper sharks, which are slow-moving predatory fish found in the deep ocean, may gather to feed on the carcass. Amphipods, crustaceans similar to shrimp, swarm over the body in enormous numbers, consuming the soft tissue. It is not uncommon for hundreds of thousands of amphipods to cover a single large whale carcass, turning parts of the whale's body white with their numbers. But as the easily consumed soft tissue is consumed, a slower process begins. The skeleton, which is largely made of bone and cartilage, is harder to consume. Some organisms specialize in eating bone. Certain species of mollusks, clams, and mussels bore into the bone of the whale, consuming it grain by grain. Other organisms specialize in consuming the lipids, the fats, that are stored within the bone. Because whales are warm-blooded and need large energy reserves to maintain their body temperature, their bones are particularly rich in lipids. For organisms living in an environment where food is almost always scarce, a whale's bone marrow represents an extraordinarily abundant energy source. The whale fall process unfolds over years or decades. In the first months and years, visible scavengers consume the soft tissue and then depart. In the following years, specialist organisms work on the bone. And after even that is consumed, the remaining minerals and the products of decomposition support a community of bacteria and other microorganisms that feed on the remnants. But even after the whale itself is completely consumed, the impact of the whale fall continues. The whale's body has altered the chemistry of the surrounding sediment, has enriched the water with the products of decomposition, has created a local area of higher nutrient concentration than the surrounding abyssal plain. This enriched area attracts organisms and supports bacterial growth for decades after the whale's body has been completely consumed. In essence, a single whale death can support an entire community of deep-sea organisms for years or decades. For organisms living in an environment where food is so scarce that they might go months between meals, the arrival of a whale fall is like a feast appearing in a desert. Some organisms have evolved specifically to exploit whale falls, living nomadic lives, moving from one whale fall to another, arriving as soon as a new whale carcass reaches the bottom and departing when the resources are exhausted. The importance of whale falls to deep ocean ecology is only beginning to be understood. Many of the organisms that specialize in whale falls have not been thoroughly studied. Some species of whale fall specialist organisms may not yet have been discovered. The ecological role that whale falls play in supporting deep-sea communities is profound, suggesting that in an ecosystem where prey is scarce, the occasional large food source that appears unpredictably can shape the evolution and behavior of an entire community of organisms. The ocean's conveyor belt, also called the thermohaline circulation, is one of the most important oceanographic features on Earth. It is a global system of ocean currents that is driven by differences in temperature and salinity, that moves water throughout all the world's oceans, that distributes nutrients and heat, and that plays a crucial role in regulating Earth's climate. The thermohaline circulation works like this. In the polar regions, water that is cold and salty sinks because it is denser than warmer, fresher water. This sinking water flows toward the equator at depth, driven by pressure gradients and the Coriolis effect. As this deep water flows toward the equator, it warms slightly and mixes with other water masses. Near the equator and at lower latitudes, some of this water rises back toward the surface, a process called upwelling, which brings deep, nutrient-rich water to the surface where photosynthesis can occur. This circulation system has been operating for millions of years, and it is crucial for life in the ocean. The upwelling brings nutrients to surface waters where they are used by phytoplankton, which forms the base of ocean food webs. The circulation of water distributes heat from the equator toward the poles, moderating Earth's climate. The deep currents carry oxygen throughout the ocean, supporting the survival of organisms even in the deepest regions. But the thermohaline circulation is not constant. It varies over time, it is affected by changes in ocean temperature and salinity, and it is slowing down. Studies of ocean currents in recent decades have shown that the Atlantic meridional overturning circulation, the part of the global conveyor belt that is most crucial for the climate of the Northern Hemisphere, has slowed by about 15% over the past century and a half. This slowing is a response to changes in ocean conditions caused by global warming. As the polar regions warm, less water sinks, because the water is warmer and therefore less dense. As glaciers melt and fresh water is added to the ocean, the salinity of water in the polar regions decreases, again making it less dense and less likely to sink. Both of these effects reduce the driving force of the thermohaline circulation, causing it to slow. The implications of a slowing thermohaline circulation are profound. If the circulation slows significantly, it could reduce the upwelling that brings nutrients to surface waters, potentially reducing ocean productivity and the amount of food available for marine life. It could reduce the distribution of oxygen to the deep ocean, creating larger regions of oxygen-poor water where few organisms can survive. It could disrupt the climate patterns that depend on the current system, potentially causing regional cooling in Europe and other regions that have been warmed by the heat-transporting effects of the thermohaline circulation. The thermohaline circulation is sometimes described as the ocean's conveyor belt, but it might be more accurate to think of it as the ocean circulatory system, analogous to the blood circulation system of animals. Just as disrupting blood flow in an animal can have serious health consequences, disrupting the thermohaline circulation in the ocean can have serious consequences for ocean health and for the climate of the planet. And we are disrupting it. Not intentionally, but as a consequence of burning fossil fuels and increasing atmospheric carbon dioxide, which warms the planet and changes ocean conditions. The changes are happening slowly, measured in terms of human perception, but rapidly in terms of oceanographic timescales. The conveyor belt that has been operating steadily for millions of years is changing in just the few decades that humans have been intensively studying it. The geological history of the ocean is written in the sediments that cover the ocean floor. Sediments are particles of rock and shell and other material that accumulate on the ocean bottom, layer by layer, year by year, century by century. These sediments preserve a record of the ocean's past, allowing scientists to reconstruct what the ocean was like millions of years ago, what the climate was like, what organisms were present, what conditions existed. The processes that generate sediments are diverse. Some sediments come from the erosion of continents, transported to the ocean by rivers and currents. Some sediments are produced by the shells and skeletons of marine organisms, calcium carbonate structures that accumulate on the ocean floor when the organisms die. Some sediments are volcanic, produced by underwater volcanic eruptions. And some sediments have chemical origins, produced by reactions in the water that cause minerals to precipitate out and accumulate. The rate at which sediments accumulate varies greatly depending on location. In areas near the mouths of large rivers, sediments can accumulate at rates of several feet per year. In the open ocean far from any continental source, sediments accumulate much more slowly, at rates of just a few millimeters per year or even less. But everywhere on the ocean floor, sediments are accumulating, slowly building up over time. Scientists study these sediment layers by drilling cores into the ocean floor, extracting long cylinders of sediment that preserve the accumulated material of thousands or millions of years. By analyzing the composition of these cores, scientists can determine what the ocean was like at different times in the past. The size and composition of particles tells us about the intensity of currents at the time. The abundance of certain fossils tells us about the temperature and productivity of the ocean. The abundance of different chemical compounds tells us about the oxygen content of the water, about whether the ocean was anoxic or well oxygenated, about the salinity and temperature of ancient seas. Using these techniques, scientists have been able to reconstruct the history of the ocean for hundreds of millions of years. We know about ice ages and warm periods, about times when the ocean was oxygen-poor and vast areas were dead zones, about periods of high productivity and periods of low productivity. We have recovered evidence of past extinction events, times when vast numbers of species disappeared from the planet. We have evidence of times when the ocean itself changed dramatically, as when continents drifted into different configurations or when ocean currents shifted due to changes in land masses or climate. The sediment record has also provided evidence about much shorter timescale changes. The impacts of human activity on the ocean can be detected in sediment cores, in the form of increased levels of pollutants, changes in the composition of shells, which reflects changes in ocean chemistry, and changes in the abundance and distribution of organisms. Perhaps most importantly, the sediment record has shown us that the ocean is not a static environment. It has changed dramatically in the past, it is changing now, and it will continue to change in the future. What is remarkable and concerning is the rate of change that is occurring now. The changes happening to the ocean today, the warming, the acidification, the disruption of ecosystems, all of these are happening faster than the changes documented in the sediment record for the past several million years. The ocean is not just changing. It is changing more rapidly than it has changed in an extraordinarily long time. The relationship between the deep ocean and the atmosphere is one of the most important relationships on Earth, a relationship that determines the climate of the planet and the composition of the air we breathe. The ocean and the atmosphere exchange carbon dioxide constantly. Carbon dioxide in the air dissolves in seawater at the surface, and carbon dioxide in seawater is released back into the air at the surface. When carbon dioxide dissolves in seawater, it forms carbonic acid, which lowers the pH of the water, making it more acidic. This process, ocean acidification, is one of the most serious consequences of increasing atmospheric carbon dioxide levels. As humans burn fossil fuels and release more and more carbon dioxide into the atmosphere becomes richer in carbon dioxide, more carbon dioxide dissolves into the ocean, and the ocean becomes more acidic. The ocean has a remarkable capacity to buffer changes in pH, to resist the acidification that would result from the dissolution of carbon dioxide. Carbonate ions in seawater react with hydrogen ions produced by the dissolution of carbon dioxide, preventing the pH from dropping as much as it would otherwise. But this buffering capacity is not unlimited. As more and more carbon dioxide is dissolved, the buffering system becomes overwhelmed and the pH drops more significantly. The consequences of acidification are severe for many organisms. Organisms that build shells or skeletons out of calcium carbonate, such as mollusks, echinoderms, and corals, are particularly vulnerable. In acidified seawater, the calcium carbonate structures that these organisms build begin to dissolve, even while the organism is still alive. Some pteropods, small swimming snails that are important food sources for fish and whales, have been observed with partially dissolved shells in areas where acidification is occurring. But acidification does not only affect shell-building organisms. It affects all marine organisms by changing the basic chemistry of their environment. Enzymes and proteins in living cells are sensitive to pH, and changes in pH can disrupt their function. Fish gills are affected by acidification. Some fish show reduced ability to detect predators or to find food when exposed to acidified water. Some fish show changes in behavior that make them more vulnerable to predation. The ocean has already become 10% more acidic over the past 200 years, a change that is significant and measurable. If current trends continue, the ocean will become even more acidic in the coming decades and centuries. Some projections suggest that the pH of the surface ocean could drop by another 30% by the end of this century if greenhouse gas emissions are not reduced. This would make the ocean more acidic than it has been at any time in millions of years, during a period covering the entire evolutionary history of most organisms living in the ocean today. The implications are profound. Organisms have adapted to the specific pH of seawater that existed for the past few million years. A rapid change in pH is a change in the fundamental nature of the environment. Organisms that have no evolutionary experience with rapid pH change, that have no adaptations for dealing with more acidic water, will struggle to survive. Some will adapt, but many will not. And many organisms that depend on other organisms that cannot adapt will also suffer as a result. Ocean acidification is not the only consequence of increasing atmospheric carbon dioxide. It is one of several interconnected changes that are transforming the ocean in real time, before our eyes, in a way that has not occurred for millions of years. The water cycle, the movement of water between the ocean, the atmosphere, and the land, is one of the fundamental processes that make life on Earth possible. The ocean plays a crucial role in this cycle. It is the source of most water that evaporates from the Earth's surface, and it is the destination for most water that falls as precipitation on land and flows back to the ocean through rivers. But the role of the ocean in the water cycle goes beyond simply being a reservoir and a source. The ocean also modulates the water cycle, moderating the intensity of precipitation and the flow of water on land. Ocean temperatures influence how much water evaporates, which in turn influences how much water precipitates as rain or snow. Ocean currents distribute heat, warming some regions and cooling others, which influences rainfall patterns. The deep ocean plays an important role in this modulation, though not in an obvious way. The deep ocean circulates slowly, taking centuries or even longer to complete a full cycle through all the world's oceans. When water descends to the deep ocean, it carries with it dissolved gases, heat, and nutrients from the surface. The deep ocean stores this heat and these gases for centuries, buffering the variations in the surface ocean and the atmosphere. As the climate warms, the water cycle is changing. Warmer air can hold more moisture, so in many regions, precipitation is becoming more intense, with heavier rainfall and more severe storms. The patterns of rainfall are also changing, with some regions experiencing more precipitation and others experiencing drought conditions. The movement of water from the land back to the ocean is changing, with some rivers carrying more water due to increased snowmelt from warming mountains, while other rivers are drying up due to decreased snowfall and increased evaporation. These changes in the water cycle are affecting not only the land but also the ocean. Changes in the amount of fresh water flowing into the ocean affect salinity, which affects water density, which affects the thermohaline circulation. Changes in the intensity of rainfall can affect the nutrient content of coastal waters, with implications for ocean productivity. And the overall warming of the ocean affects the rate of evaporation and the patterns of atmospheric circulation. The ocean's role in the water cycle is one of the least visible but most important roles that the ocean plays. It is difficult to see the effects of the ocean's modulation of the water cycle from day to day. But over seasons and years, the influence becomes apparent, as regions experience rainfall patterns that are influenced by distant ocean temperatures and currents. And as the ocean changes, as it warms and becomes stratified and circulates differently, the patterns of precipitation on land are changing in response. These changes in water distribution, both on land and in the ocean, will have profound impacts on human societies. Regions that have been arid for millennia may face increased rainfall, while regions that have been the breadbasket of civilizations may face increased drought. The changes will not happen uniformly or predictably. Instead, they will happen with localized intensity, with some regions facing extreme changes while others experience only modest changes. And all of these changes will happen in real time, over the course of decades, forcing human societies to adapt to a hydrological system that is fundamentally different from the stable system that supported the development of civilization. The relationship between sunlight and the deep ocean is one of the most fundamental relationships in oceanography, and yet it is also one of the most counterintuitive. Sunlight does not reach the deep ocean. The deep ocean is in perpetual darkness. And yet, virtually all of the life in the deep ocean ultimately depends on the sunlight that falls on the surface of the ocean thousands of feet above. This relationship is mediated by what is called the biological pump. The biological pump is the process by which carbon dioxide from the atmosphere is fixed by photosynthetic organisms in the surface ocean, incorporated into the bodies of these organisms, and then transported to the deep ocean when these organisms die and sink. Here is how it works. Phytoplankton in the surface ocean use sunlight and carbon dioxide to produce organic matter. When these phytoplankton die, they sink. As they sink, they are consumed by other organisms, zooplankton that feed on the phytoplankton. When these zooplankton die, their bodies also sink. The process continues, with larger organisms consuming smaller organisms, all of them eventually sinking toward the bottom as dead particles. By the time these particles reach the deep ocean, a significant portion of the original carbon has been consumed and respired by organisms at intermediate depths. But a substantial fraction survives the journey and reaches the deep ocean floor as a slow but steady rain of organic particles. This rain of organic matter is the primary food source for most deep-sea organisms. Without this rain, the deep ocean would be biologically dead. The significance of the biological pump extends beyond supporting deep-sea life. The biological pump is a crucial component of the global carbon cycle. Carbon dioxide in the atmosphere is fixed by phytoplankton, transported to the deep ocean, and deposited on the seafloor as organic matter or as calcium carbonate shells. If it were not for the biological pump, much of the carbon dioxide that has been released into the atmosphere by human activities would still be in the atmosphere, the concentration would be even higher than it is now, and the greenhouse warming would be even more severe. But the biological pump is not infinitely efficient. Not all of the carbon that is fixed by phytoplankton in the surface ocean reaches the deep ocean. Some is respired back to carbon dioxide in the surface layers. Some is consumed by surface predators and held in the upper water column. And the efficiency of the biological pump varies depending on conditions. In nutrient-rich regions where productivity is high, more carbon sinks to the deep ocean. In nutrient-poor regions where productivity is low, less carbon sinks. Changes in ocean productivity, driven by changes in nutrient availability, ocean temperature, and other factors, affect the efficiency of the biological pump. If the biological pump becomes more efficient, more carbon is transported to the deep ocean. If it becomes less efficient, less carbon is transported. And this change in the efficiency of the biological pump can, in theory, feed back on atmospheric carbon dioxide levels, affecting the rate of climate change. The deep ocean's role in the biological pump means that the deep ocean is not separate from the surface ocean and the atmosphere. They are connected through the constant rain of organic matter, through the circulation of water and nutrients, through the chemistry of carbon dioxide and other gases. The deep ocean is, in a very real sense, the lungs of the Earth, breathing in and breathing out carbon, storing it for centuries in the cold depths and then slowly releasing it back to the atmosphere when the deep water eventually rises again toward the surface. The abyssal plains, the vast flat areas of the ocean floor that lie between 2,000 and 3,000 feet below the surface, cover a larger area of the Earth than all of the continents combined. These plains are essentially the deserts of the deep ocean, places where food is extraordinarily scarce and organisms must make do with extremely limited resources. But the abyssal plains are not truly lifeless, nor are they even sparsely inhabited. They support entire communities of organisms adapted to live under these extreme conditions of scarcity and isolation. The density of life on the abyssal plains is low, but life is present. Bacteria cover the sediments. Small crustaceans crawl across the bottom. Small fish hover above the sediment, hunting for prey. And filter feeders that strain particles from the water wait patiently for the next fragment of organic matter to drift down from above. One of the most characteristic organisms of the abyssal plains is the tripod fish. The tripod fish is a small fish, just a few inches long, that has evolved a remarkable adaptation to life on the abyssal plains. The fish has extremely long fin rays that it uses to prop itself up off the bottom of the ocean, allowing it to hold its body above the sediment. The fish orients itself so that it faces into the current, allowing the current to bring food particles directly to its mouth. The fish simply waits, expending minimal energy, for food to come to it. The tripod fish is one of the most successful inhabitants of the abyssal plains, and its strategy of waiting rather than hunting is a perfect adaptation to an environment where food is scarce and energy conservation is critical. Another characteristic organism of the abyssal plains is the sea cucumber. Sea cucumbers are echinoderms, relatives of starfish and sea urchins, that have evolved into elongated, slug-like forms. Sea cucumbers feed by moving slowly across the sediment, ingesting mouthfuls of sediment and extracting the organic particles and microorganisms contained within it. In some areas of the abyssal plains, sea cucumbers are so abundant that they cover the bottom, creating a landscape of small rounded humps across the otherwise smooth sediment. The abyssal plains are also inhabited by a variety of other organisms: crustaceans, mollusks, sponges, anemones, and countless other species that have found ways to survive in an environment that appears to offer almost nothing to support life. And yet, these organisms have persisted for millions of years, have evolved into unique forms adapted to these specific conditions. The abyssal plains are changing, though the changes are subtle and slow. As the ocean warms and becomes more acidic, the conditions of the abyssal environment are changing. The rate at which organic matter sinks from above may change as surface productivity changes in response to warming. The chemistry of the water may shift in ways that affect organisms adapted to the specific chemistry that has existed for millions of years. These changes are particularly concerning because the abyssal plains support such specialized communities. The organisms that live there have had millions of years to adapt to the specific conditions of the abyssal environment. They have no evolutionary experience with rapid change, no flexibility to adapt to radically different conditions. If the abyssal plains change significantly, the specialized communities that have evolved to live there may not be able to adapt. And if these communities collapse, we may not even notice, because the abyssal plains remain largely invisible to human observation. The ocean floor is not static. It moves, albeit incredibly slowly, driven by the processes of plate tectonics. The Earth's lithosphere, the hard outer layer of the planet, is divided into plates that drift across the surface over geological time. These plates collide with each other, slide past each other, and diverge from each other. Where plates diverge, new ocean floor is created. Where plates collide, old ocean floor is pushed down into the mantle and destroyed. This process, called seafloor spreading and subduction, has been reshaping the ocean floor for billions of years. The evidence for this process is visible in the composition and age of the ocean floor. The ocean floor near mid-ocean ridges, where new ocean floor is created by the upwelling of hot mantle material, is young, sometimes just a few million years old. The ocean floor far from mid-ocean ridges, near the edges of continents or in isolated basins, is older, sometimes hundreds of millions of years old. The oldest ocean floor on Earth is no more than about 250 million years old, which means that the entire ocean floor is younger than the oldest rocks found on continents. The continuous creation and destruction of ocean floor has profound implications for the organisms that live on the ocean floor. Hydrothermal vents, found primarily at mid-ocean ridges where new ocean floor is being created, appear and disappear on geological timescales. An active vent system may remain active for thousands or tens of thousands of years, but in geological terms this is a brief moment. When a vent system becomes extinct, the entire community of organisms adapted to that vent system may become extinct with it, unless some individuals manage to disperse and colonize a new vent system. The creation of new ocean floor also changes the shape of ocean basins, which affects ocean circulation and nutrient distribution. The position of continents, which is constantly changing due to plate tectonics, determines where water can flow and where barriers exist to ocean circulation. Over millions of years, as continents drift into different configurations, the global ocean circulation patterns change in response, which changes the distribution of nutrients and heat, which changes the distribution of organisms. The fossils found in ocean sediments provide evidence of these changes. In sediment cores, we find the remains of organisms that prefer warm water mixed with the remains of organisms that prefer cold water, evidence that the climate and the ocean circulation patterns have changed over time. We find organisms that prefer nutrient-rich water in layers where the sediments also indicate that nutrient-rich water was present. We find evidence of past extinction events that appear to correlate with changes in ocean circulation patterns or with catastrophic events like volcanic eruptions or impacts of asteroids. Understanding the deep history of the ocean, the changes that have occurred over millions of years, provides perspective for understanding the changes that are occurring now. The ocean has changed dramatically in the past. Circulation patterns have shifted, productivity has gone up and down, organisms have appeared and disappeared. But the rate of change that we are seeing now is unusual. The changes happening to the ocean today are occurring many times faster than the average rate of change preserved in the geological record. This rate of change is one of the primary concerns about the future of the deep ocean and the organisms that inhabit it. The discovery of life around hydrothermal vents was a paradigm shift in our understanding of what life on Earth requires and where life can exist. Before that discovery, scientists believed that virtually all life on Earth ultimately depends on the sun, on photosynthesis, on the energy that flows from sunlight captured by plants and transmitted through food webs to all other organisms. The existence of chemosynthetic ecosystems around hydrothermal vents showed that this assumption was wrong. Life could thrive in places where no sunlight ever reaches, where the only energy source is the chemical energy released by reactions between minerals in hot vent water and oxygen in the surrounding ocean water. The implications of this discovery extended far beyond understanding deep-sea life. It changed how scientists think about the possibility of life on other worlds. Europa, a moon of Jupiter, is covered with ice but is believed to have liquid water beneath the ice, in an ocean that could be several times deeper than the Earth's oceans. Europa receives virtually no sunlight. Its surface temperature is hundreds of degrees below freezing. And yet, if the interior of Europa is warm enough, if the interaction between the rocky interior and the water creates the right chemical conditions, Europa could potentially host chemosynthetic life similar to what exists around hydrothermal vents on Earth. Similarly, Enceladus, a moon of Saturn, has water jets erupting from its icy surface, evidence that there is a subsurface ocean beneath the ice. The chemical composition of these water jets suggests that there may be hydrothermal activity in the ocean beneath the ice. If so, Enceladus could potentially host chemosynthetic life. Other moons and dwarf planets in the outer solar system could also have subsurface oceans with chemosynthetic ecosystems. None of this requires the existence of photosynthesis, solar energy, or any of the other characteristics we associate with life on Earth. It requires only liquid water, chemical energy sources, and time. And if life based on chemosynthesis can exist on Earth in the deep ocean, there is no reason it could not exist in similar environments on other worlds. The question of whether life actually exists on other worlds remains unanswered. But the discovery of chemosynthetic life on Earth has expanded the boundaries of where we might look and what we might find. It has suggested that the universe could be more alive than we previously imagined, filled with organisms thriving in environments that we might not initially recognize as hospitable to life. This is one of the great gifts of studying the deep ocean. By understanding the extreme life that exists in the deepest, darkest, most hostile parts of our own planet, we understand more about what life is, how far it can stretch, how creative and adaptable and persistent it can be. And this understanding helps us imagine what life might exist in other places, in other worlds, in the vast universe beyond our own planet. If you were to suddenly find yourself on the ocean floor at a depth of 3,000 feet or more, the first thing you would notice is the cold. The temperature of the deep ocean is just a few degrees above freezing, and it is stable, constant, unchanging. Your body would lose heat rapidly. Within minutes, you would be dead, even if the pressure did not crush you instantly, even if you were not breathing water, even if the complete darkness did not drive you mad. The second thing you would notice, or rather what you would not notice, is the absence of sound in the way you understand sound. Sound travels through water, but the frequencies that humans perceive are not prevalent in the deep ocean. The deep ocean is often described as silent by humans who have been there, but this is a misconception. The deep ocean is filled with sound, but it is sound at frequencies and intensities that human ears cannot perceive. The creaks and groans of the Earth's crust, the sounds of organisms communicating with each other, the movement of water through the vast spaces of the ocean, all of these produce sound that fills the deep ocean, but that a human would perceive as silence. The third thing you would notice is the pressure. The pressure in the deep ocean is not something you can easily describe in human terms. It is not painful in the way that a crush injury is painful. It is not a sensation at all, in the way that humans understand sensation. It is, instead, a complete alteration of the environment in which you exist, changing how your body functions, how your senses perceive, how your very atoms are organized and interact. If you were brought to the deep ocean in a pressure suit, protected from the physical effects of the environment, you would notice the darkness. The darkness in the deep ocean is not the darkness of a cloudy night or the inside of a cave. It is a darkness so complete and so total that it is almost impossible to imagine from the surface. It is the darkness of a place where light has never reached, where even the faintest glow from the sun has been filtered out by miles of water above. And in that darkness, life continues. Organisms hunt and eat and reproduce and die. They carry out all of the basic functions of life in an environment that no human could survive in unprotected for more than a few minutes. Their lives are lives lived in conditions that no human has any intuitive understanding of. Their existence is utterly alien to everything we know about our own existence, and yet they are as real, as alive, as conscious in their own ways as any human. The deep ocean is a world that exists beyond human comprehension in many ways. We can study it, we can send instruments to record data from it, we can even visit it in submarines. But we can never truly live in the deep ocean the way the organisms that inhabit it live. We can never truly understand what it is like to be a deep-sea creature, to exist in those conditions as a normal state of being. And yet, despite this fundamental alienness, the deep ocean is our ocean. It is part of our planet, part of our biosphere, part of the system that supports our own existence. What happens in the deep ocean affects the surface ocean. What happens to deep-sea organisms affects the entire ocean food web. The fate of the deep ocean is the fate of every human who depends on the ocean for food, for climate stability, for the continuation of the planet as we know it. The concept of time operates differently in the deep ocean than it does in the surface world. On land and at the surface of the ocean, time is marked by the passage of day and night, by the seasons changing, by the migration of animals and the growth of plants. The passage of time is visible, measurable, obvious. In the deep ocean, time passes at a different scale. The day-night cycle exists only as a faint signal, detectable only as the smallest change in the abundance of certain particles or the behavior of certain organisms. The seasons exist, but their effects are muted and delayed. Some organisms respond to seasonal changes, but the signal is weak and the response is slow. Instead, deep-sea organisms seem to exist on a geological timescale. Changes happen slowly, on scales of months or years or decades. The growth of a deep-sea organism might be slow enough that you could not visibly detect growth happening even if you were watching the organism continuously. The reproduction of a deep-sea organism might occur only once every few years, or once every few decades in the case of some species. But the slowness of biological time in the deep ocean is not laziness or a failure to adapt. It is an adaptation to the conditions of the environment. When food is scarce, when the energy required to find and consume food is high, when the risk of being injured in the search for food is substantial, the optimal strategy is to move slowly, to rest for long periods, to use energy only when necessary. The slowness is an efficiency, a way of living that maximizes the chance of survival in an environment where the opportunities for feeding are infrequent and unpredictable. This slow time of the deep ocean is one of the reasons that the deep ocean is so vulnerable to rapid change. When environmental conditions change, deep-sea organisms need time to respond. They need time to adapt, to change their behavior, to migrate to new areas. But if the environmental changes are happening faster than these organisms can respond, if the changes are occurring on timescales of years or decades rather than thousands or millions of years, then the organisms may not be able to keep up. The fast time of human civilization, the rate at which we change our environment, build new technologies, and rearrange the world, is completely incommensurate with the slow time of the deep ocean. A change that happens in a few years can take the deep ocean millions of years to recover from, if it can recover at all. This mismatch in timescales is one of the fundamental reasons why human impacts on the deep ocean are so significant and so concerning. The exploration of the deep ocean has advanced dramatically in recent decades due to the development of new technologies. Autonomous underwater vehicles, robotic submarines that can operate without a human pilot, have made it possible to explore vast areas of the ocean without risking human lives. Deep-sea cameras, capable of operating at pressures that would destroy conventional cameras, have made it possible to observe and film the organisms and the environments of the deep ocean in unprecedented detail. But for all the advances in technology, the deep ocean remains largely unexplored. The vast majority of the deep ocean has never been directly observed by humans or by human instruments. The organisms that live there have not been catalogued. The ecosystems have not been fully mapped. The distributions of species are not fully known. In many ways, the deep ocean is as unexplored as the surface of another planet would be. This lack of exploration is partly due to the extreme difficulty of exploring the deep ocean. It is expensive to send an expedition to the deep ocean, to maintain equipment that can withstand extreme pressures, to process and analyze the data that is collected. It is time-consuming, because the speeds at which underwater vehicles can travel are slow, and the distances involved are vast. And it is dangerous, even with modern safety technologies, to send people or equipment into an environment as hostile as the deep ocean. But the lack of exploration also reflects, in some sense, a lack of priority. Until recently, the deep ocean was not considered to be particularly important to understand. The deep ocean did not support human fisheries in the same way that surface waters did. The deep ocean did not contain resources that were economically valuable in the way that surface resources were. The deep ocean did not contain species that humans hunted or consumed. Therefore, the deep ocean was not studied as intensively as other parts of the ocean or the Earth. This neglect is changing, as the realization grows that the deep ocean is not separate from the rest of the planet, that it does matter what happens in the deep ocean, that it does matter what organisms live there and how they are affected by human activities. Scientific funding for deep-sea research has increased in recent years. New technologies are being developed that make deep-sea exploration more feasible and more affordable. Expeditions to the deep ocean are becoming more frequent. But we may already be too late to fully understand the deep ocean before we transform it beyond recognition. Some deep-sea ecosystems are being destroyed by fishing trawls before they have even been discovered. Some deep-sea species are being driven to extinction before they have been described by science. The window for discovering and understanding the deep ocean before we fundamentally alter it is closing. This is not a problem that has an easy solution. The resources required to fully explore and map the deep ocean are vast. The time required is substantial. But the potential cost of not doing so, of destroying deep-sea ecosystems and driving species to extinction without ever understanding what we are destroying, is profound. The deep ocean may be the last great frontier on Earth, but if we do not explore it soon, the frontier will be gone before we have a chance to really see what is there. The relationship between humans and the ocean has been fundamental to human civilization since the beginning of recorded history. Humans have used the ocean for food, for transportation, for commerce, for spiritual meaning. Entire civilizations have been built around ocean fishing. Cities have risen on the coasts of oceans. Wars have been fought over access to marine resources. The ocean has been the source of human prosperity and the site of human tragedy. But the ocean that existed for the vast majority of human history was the surface ocean, the waters above the deep. Humans fished the surface waters, sailed the surface waters, threw waste into the surface waters, but remained fundamentally ignorant of the deep. The deep ocean was a mystery, a realm of myth and legend, a place that existed mostly in the imagination. This ignorance provided a kind of protection for the deep ocean. Because humans did not know what was there, could not reach it easily, did not have resources there to exploit, the deep ocean could continue to function in its own way, undisturbed by human activity, isolated from human impact. The deep ocean could be a refuge, a place where evolution continued unchecked by human influence, where ecosystems could develop and persist according to their own logic rather than the logic of human economic interests. But this protection is eroding as human technology advances. Where we once could not reach the deep ocean, we now can. Where we once could not exploit the deep ocean, we now are developing technologies that make exploitation possible. Where once the deep ocean was simply too distant and too difficult to be worth human effort, now human economic interests are focusing on the deep ocean because other resources have become depleted or because new technologies have made deep ocean resources more accessible. This is a transition point in the history of human interaction with the ocean. We are crossing a threshold from an era of deep ocean ignorance to an era of deep ocean exploitation. And as this transition occurs, the protection that isolation provided is disappearing. The deep ocean is being included in the human economic system. The organisms of the deep ocean are being caught and killed for food or for other purposes. The deep ocean floor is being mined or is being proposed for mining. The water itself is being changed by the absorption of excess heat and carbon dioxide from the atmosphere. The question facing humanity is not whether we will have an impact on the deep ocean. That is inevitable. The question is what kind of impact we will have, how severe it will be, whether we will attempt to manage our impact to preserve some of the deep ocean's current characteristics, or whether we will allow the deep ocean to be transformed completely into a resource zone, a place whose only value is the value of the resources it contains. This decision, whether made explicitly or implicitly through a series of smaller decisions, will determine the fate of the deep ocean for centuries or longer. It will determine whether future generations have access to the richness and mystery of the deep ocean, or whether the deep ocean becomes merely another industrialized zone, another part of the human economic system, stripped of its most remarkable features, transformed into a simplified, human-dominated landscape. The sense of wonder that comes from contemplating the deep ocean is not merely an aesthetic response. It is something deeper, something that touches on fundamental aspects of human cognition and human psychology. Humans have an innate need to understand the world around them, to map it, to categorize it, to incorporate it into a coherent worldview. When we encounter something that is radically strange, that does not fit into our existing categories, that is so different from our everyday experience that we struggle to comprehend it, we experience a kind of cognitive challenge. But we also experience fascination. The deep ocean is radically strange. It is fundamentally different from any environment that humans have direct experience with. The darkness, the pressure, the cold, the slow metabolism of the organisms, the minimal food supply, the strange adaptations that organisms have evolved to cope with these conditions, all of these are so far removed from human experience that they are almost incomprehensible. And yet, we can study the deep ocean, we can learn about it, we can come to understand it, at least in some basic way. This process of learning about something radically strange, of building understanding of a world that is almost completely alien to our own direct experience, seems to be something that humans find deeply satisfying. It is part of what drives exploration, that impulse to go where humans have not been, to see what humans have not seen, to understand what humans do not currently understand. But there is something more at stake in the case of the deep ocean. The deep ocean is not merely something fascinating to understand. It is something that is intrinsically valuable, that has value independent of whether humans understand it or appreciate it. The organisms of the deep ocean have intrinsic value. They exist, they live, they respond to their environment, regardless of whether any human is aware of their existence. And this intrinsic value, this existence that does not depend on human awareness or human appreciation, is something that many people find meaningful and important. There is also an aesthetic dimension to the deep ocean that is worth noting. Even if we never visit the deep ocean in person, even if we never see with our own eyes the bioluminescent creatures or the strange adaptations of the organisms that live there, the knowledge that these things exist, that this world exists beneath the surface of the oceans that cover our planet, provides a kind of beauty and a kind of meaning. It is a beauty that comes from understanding, from knowing that reality is far richer and far more complex and far more strange than our everyday experience suggests. This sense of wonder and meaning is something that seems to be necessary for human well-being. Studies have shown that people who feel a sense of connection to nature, a sense of awe and wonder at the natural world, are happier and healthier than people who do not. The deep ocean, with all its strangeness and all its complexity, provides an opportunity for this sense of connection and awe. And as the deep ocean is degraded and transformed, as the organisms that live there are driven to extinction, as the ecosystems are destroyed, something important is lost that goes beyond the mere loss of species or ecosystems. The paradox of the deep ocean is that it is both enormously important and largely invisible. The deep ocean influences the climate of the planet, influences the composition of the atmosphere, influences the distribution of nutrients that support all ocean life, and yet most people go through their entire lives without ever thinking about the deep ocean or realizing that it exists. This invisibility is not accidental. The deep ocean is out of sight, beneath the surface of the water, at depths that are unreachable by most humans. The organisms that live there are not visible to the human eye in any normal circumstances. The events that occur in the deep ocean are not perceived through human senses. The deep ocean is, in a very real sense, a hidden world. This hiddenness creates a problem for conservation and for the protection of the deep ocean from human impacts. In general, people care more about things that they can see, that they have direct experience with, that are visible in their daily lives. A forest that is being destroyed is visible, and people can see the trees being cut down and feel a sense of loss or urgency about preserving the forest. But a deep-sea ecosystem that is being destroyed is invisible. The fishing trawls are not visible. The organisms that are being killed are not visible. The damage to the ecosystem is not visible. And so, for most people, the destruction of the deep-sea ecosystem is not real, not urgent, not worthy of attention. This creates an unfortunate situation where the places that are most important, that have the most influence on the planet systems, are also the places that are least visible and therefore least protected by public concern. People are motivated to protect the Amazon rainforest because they can see its value, because it is visible and iconic. But the deep ocean, which may be equally important for the functioning of the planet's climate and its biogeochemical cycles, is largely invisible and therefore less protected, despite its importance. Changing the situation requires making the deep ocean visible, making it real to people through stories and films and images, making people understand that the deep ocean exists, that it is remarkable, and that it is being affected by human activities. It requires developing a kind of environmental consciousness that extends beyond the visible world, that recognizes the value of things that are hidden and hard to see. And it requires that this consciousness be acted upon, that it be translated into policies and practices that protect the deep ocean from destructive human activities. This is a challenge because the deep ocean is not an easy thing to visualize or understand without direct experience. It is not an easy thing to care about if you have never seen it and cannot easily imagine what it is like. But the challenge of making the invisible visible, of creating care for the things that are hidden, is one that humanity will need to meet if we are to have any hope of protecting the deep ocean for future generations. The ocean does not only receive, it also returns. It returns oxygen, with approximately 50% of the oxygen that we breathe being produced by photosynthesis of phytoplankton in the ocean. It returns water in the form of evaporation that feeds the hydrological cycle and produces the rain that falls on continents. It returns proteins in the form of fish that feeds more than 1 billion people in the world. It returns medicines, as we have seen, in the form of bioactive compounds from its organisms. It returns beauty, in every coastal culture that has found in the sea a source of inspiration for art, literature, and music. And it returns something else that is harder to quantify but equally real: perspective. The perspective that comes from contemplating something that is larger and older than any immediate problem or concern. The perspective that comes from knowing that beneath the waters that border the continents exists a world that does not know we exist, that does not need us, that has been functioning with extraordinary complexity and efficiency for millions of years before we appeared and will continue to do so, with or without our help, for millions of years after we have gone. This perspective does not produce indifference. It produces, if cultivated well, a kind of humility that is also a kind of respect. Respect for a system that is far more complex than we understand, that functions according to rules we do not yet fully know, and that deserves to be treated with the caution that is appropriate for what we do not completely comprehend. The ocean tonight is doing what it always does. Its currents circulate. Its organisms eat and grow and die and are consumed. Its sediments accumulate millimeter by millimeter. Its hydrothermal vents expel hot chemicals into cold water. Its whales navigate using routes they learn from their mothers who learned them from theirs, in a chain of cultural transmission that extends across generations. And its bioluminescent creatures produce their own light in the deepest darkness, as they always have, as they always will, not knowing that there is someone looking from above with sleep approaching and darkness as companion. There is one last thing about the deep ocean that deserves to be said before sleep arrives. It is not a fact or a scientific piece of data. It is an observation about the nature of the unknown and about why it matters. The ocean floor is unknown, but it is not inert. It is not waiting passively to be discovered. It is happening, actively, in this moment, in the darkness. Hydrothermal vents are expelling hot chemicals. Bioluminescent organisms are producing light. Sediments are accumulating 1 micrometer more of history. Deep currents are moving south, east, downward. The deep ocean does not need to be known to exist. It existed for millions of years before there was any being capable of knowing it, and it will exist for millions of years after the being that currently knows it partially has disappeared. Its existence does not depend on our attention, on our instruments, on our scientific categories. But our understanding of our own world does depend on knowing it. Because the ocean floor is part of what makes this planet what it is. Its influence on climate, on biogeochemical cycles, on the distribution of living organisms, on the geological history of the planet, all of those influences operate independently of whether we understand them or not. But if we want to predict the future of the system we inhabit, if we want to manage our impact on it intelligently, if we want to avoid the mistakes we make when we act on systems we do not understand, we need to know the deep ocean much better than we know it now. This need is not urgent in the sense that something will happen tomorrow if we do not know it. It is urgent in the sense that we are already acting on the deep ocean, already warming it and acidifying it and contaminating it, without fully understanding the consequences of these actions. It is urgent in the sense that the window for knowing the ocean floor before we transform it irreversibly is closing faster than scientific exploration can advance. Tonight you cannot descend to the bottom of the ocean. No one can do so without years of preparation and millions of euros of investment. But you can carry with you the knowledge that this world exists, that it is extraordinary, that it is alive in its darkness, and that it deserves the attention and care that it has rarely received until now. Let that be enough for tonight. If this journey accompanied you tonight, subscribe to the channel. There are many more worlds waiting to be explored in the darkness.